Central limit theorem and law of large numbers are important theorems in probability theory and in practice. The central limit theorem can be used to approximate probability when the sample's number is large, even if the distribution is not calculated exactly, so that we can make right decisions. Today I'm going to talk about the proofs and the connections of central limit theorem and the law of large numbers. Let's start. First, let's review the conclusions from mirror theory. Chebyshev's inequality is often used in the proofs. It says that if we have some real and non-negative function phi, and some set A belongs to R, and I sub A is infimum of phi, then we will know that I sub A times the probability of some random variable x belongs to set A is smaller or equal to the expectation of phi of x when x is belong to A, which is smaller or equal to the expectation of phi of x. We have a corollary which may be more familiar. If x is a random variable with mean mu and variance sigma squared, then the probability of the absolute value of x minus mu is greater or equal than c is smaller or equal to sigma squared over c squared. Next, we will talk about the dominated convergence theorem. If xn goes to x almost surely, which will be explained very soon, the absolute value of xn is smaller or equal to y for all n, and the expectation of y is finite, then the expectation of xn goes to expectation of x. Also, if y is constant, then theorem 2 is called the bounded convergence theorem. Finally, we will introduce the Fubini's theorem. If f is non-negative and the integral of the absolute value of f with respect to mu is finite, then the order of the integral doesn't matter. Actually, we can prove this theorem in 4 cases. When f is the indicator function, when f is a simple function, when f is the non-negative function, and when f is any function. Next, we will show few definitions which are key in our theorems. First, Yn convergence to Yn probability means for all epsilon greater than 0, the probability of the absolute value of Yn minus y greater than epsilon goes to 0 as n goes to infinity. Second, xn converges to x almost surely, or as for short, if the probability of xn as n goes to infinity equals x is 1. Third, x1, x2, etc. are independent and identically distributed, or IID for short, if they are independent and have the same distribution. Now we are ready for the first weak law of large number. This law is the weaker case of weak law of large number. It only deals with random variable with finite variance. It states as the following: that x1, x2, etc. will be uncorrelated random variables. That is, the product of the expectation is the expectation of the product of the two variables. The variables has the expectation equals mu, and the variance is finite. As n goes to infinity, the sum over n, which is an average, goes to the expectation in probability. We can prove this law by using the condition that the variance is finite, and observe that the expectation of Sn over n is mu, so that the expectation of Sn over n minus mu squared is the variance of Sn over n by definition, and it's 1 over n squared times the sum of the variance, which is smaller or equal to Cn over n squared, because the variance is finite, which goes to 0. Notice that if p greater than 0 and the expectation of the absolute value of Zn to the p's power goes to 0, then Zn goes to 0 in probability, and we get what we want. From this theorem, we can notice a very funny thing. A high-dimensional cube is almost the boundary of a ball. If we take y is x squared, with x belongs to -1, 1, and evaluate Sn over n. Next, we will show a few definitions which are key in our theorems. First, Yn convergence to Y improbability means for all epsilon greater than 0, the probability of the absolute value of Yn minus y greater than epsilon goes to 0 as n goes to infinity. Second, Xn converges to X almost surely, or AS for short, if the probability of Xn as n goes to infinity equals X is 1. Third, X1, X2, etc. are independent and identically distributed, or IID for short, if they are independent and have the same distribution. Now we are ready for the first weak law of large number. This law is the weaker case of weak law of large number. It only deals with random variable with finite variance. It states as the following: that x1, x2, etc. will be uncorrelated random variables. That is, the product of the expectation is the expectation of the product of the two variables. The variables has the expectation equals mu, and the variance is finite. As n goes to infinity, the sum over n, which is an average, goes to the expectation improbability. We can prove this law by using the condition that the variance is finite, and observe that the expectation of Sn over n is mu, so that the expectation of Sn over n minus mu squared is the variance of Sn over n by definition, and it's 1 over n squared times the sum of the variance, which is smaller or equal to Cn over n squared, because the variance is finite, which goes to 0. Notice that if p greater than 0 and the expectation of the absolute value of Zn to the p's power goes to 0, then Zn goes to 0 in probability, and we get what we want. From this theorem, we can notice a very funny thing. A high-dimensional cube is almost the boundary of a ball. If we take y is x squared, with x belongs to -1, 1, and evaluate Sn over n. Now we are ready to prove the strong law of large numbers. We will use a trick. If we want to show that Xn over Cn goes to 1 almost surely, for sequences Xn, Cn, which are non-negative and increasing, it's enough to prove the result that for a subsequence nk that has Cnk plus 1 over Cnk goes to 1. We'll also notice that Xn can be expressed by two parts, Xn plus minus Xn minus for n greater than 1. We can, thus, without loss of generality, suppose that X1n is non-negative. We will prove the result first for a subsequence, and then use monotonicity to control the values in between. We let alpha greater than 1 and kn equals the square bracket of a to the nth power. The square bracket just means the greatest integer which is smaller or equal to an. So Chebyshev inequality implies that if epsilon is greater than 0, the sum over n of the probability of the absolute value of tkn minus the expectation of tkn is greater than epsilon kn is smaller or equal to epsilon to the negative second power, which is just the infimum, times the sum over n of the variance of tkn over kn squared, which is sum over two parts, the epsilon to negative seconds power times the sum over n of kn to negative seconds power of the sum over m, always to kn. So this sum is in the first sum of the variance of ym, which is just epsilon to the negative seconds power times the sum of variable ym's variance over m of the sum over n, which kn is greater or equal to m, of kn to the negative seconds power. Note that here it's still in this first sum, and we use Fubini's theorem to interchange the two summation of non-negative terms right over here. Now kn is the square bracket of an, and an must be greater or equal to an over 2 for m is greater or equal to 1. This is obvious. And summing the geometric sequence and noting that the first term is smaller or equal to m to the negative seconds power. So it just becomes 4, which is from lemma 2, times the sum over n, which an is greater or equal to m, of alpha to the negative 2n's power, which is smaller or equal to 4, times 1 minus alpha to the negative second power over to the negative first power times m to the negative second power, which we used the summation of the geometric sequence. We also notice that the sum is finite by lemma 2, since epsilon is arbitrary and tkn minus the expectation of tkn over kn goes to 0. Almost truly, the dominated convergence theorem applies that the expectation of yk goes to expectation of x1 as k goes to infinity. So the expectation of tkn over kn just goes to its expectation of x1. And from lemma 1, we have shown that tkn over kn just goes to the expectation of x1 almost truly. To handle the intermediate value, we observe that if kn is smaller or equal to m, which is smaller than kn plus 1 by the increasing property, tkn over kn plus 1 is smaller or equal to tm over m is smaller or equal to tkn plus 1 over kn, and yn is greater or equal to 0. So recalling kn equals the square bracket of a to the nth power, we have kn plus 1 over kn goes to a, and the expectation of x1 over a is smaller or equal to the limit of the infimum of tm over m as n goes to infinity is smaller or equal to the limit of the supremum of tm over m as m goes to infinity, which is smaller or equal to alpha times the expectation of x1. And alpha is arbitrary and greater than 1, so the proof is complete. Actually, you can prove that this result holds whenever the expectation exists easily. Now we are going to prove the central limit theorem. We need to introduce the characteristic function now, or CHF for short. Its definition is the following. If x is a random variable, its characteristic function is phi of t, which is the expectation of e to the I t x power. You can expand it by the Euler's formula, and the e is just the expectation. It has some properties. First, phi of 0 is just 1. Second, phi of negative t is the conjugate pair of phi of t. Third, the absolute value of phi of t is the expectation's absolute value, which is smaller or equal to the expectation of e to the I t x power, which is 1. The fourth one is that the absolute value of phi of t plus h minus phi of t is smaller or equal to the expectation of e to the I h x minus 1, or phi of t is just continuous on the real number line. Fifth, the expectation of e to the I t ax plus b's power is just e to the I t b times phi of at. Sixth, if x1 and x2 are independent and have the characteristic function phi1 and phi2, then x1 plus x2 have the characteristic function phi1t times phi2. The seventh, if f1 etc. have the characteristic phi1, phi2 etc. and we have non-negative lambdas and their sum is 1, then the sum over I of lambda I times f of I have the characteristic function of sum over I lambda I times phi of I. These properties can be directly got from the definition. The seventh, you should use the integral by parts, and they are very easy. Now we are going to introduce few lemmas. Lemma 1 is from Taylor theories. The absolute value of e to the ix minus the sum over m of ix to the m's power over m factorial. This is just the Taylor theories of e to the ix to the nth power is smaller or equal to the minimum of x's absolute value to the n plus 1 or n plus 1 factorial, or 2 to the x of n over n factorial. We have two corollaries from this. The first one is the expectation of this. Notice we can take the expectation to both sides. The second corollary is that if e of x squared is finite, then phi of t can be expressed by 1 plus it times the expectation of x minus t squared times the expectation of x squared over 2 plus some infinitesimally small term. To prove this, we use corollary 1 to prove the infinitesimal with respect to the second's power. Lemma 2 is that if Cn goes to C, which are complex numbers, then 1 plus Cn over n to the nth power goes to e to the C. This can be proved using the following lemma. Let Z1, Z2, etc. and W1, W2, etc. the complex number of modulus is smaller or equal to theta, then the absolute value of the product over m of Zm minus the product over m of Wm is smaller or equal to theta to the n minus 1 power times the sum over m of the absolute value of Zm minus W. This can be proved by mathematical induction. You first prove that this is true for n is 1, then you prove it for n plus 1. Now we are ready to prove the central limit theorem with finite variance. Let x1 and x2 etc. be IIDs with the expectation equals mu and variance equals sigma squared, which are non-negative and finite, and they can't be 0. If Sn is the sum, then Sn minus n times mu over sigma times the square root of n goes to the normal distribution, and this is standard normal distribution, means that mu and sigma are all 1. Proof by considering y prime equals x minus mu. It's sufficient to prove the result when the expectation is 0. From the corollary 2, we know that phi t can be expressed by 1 minus the sigma t squared over 2 plus the infinitesimally small term. So the expectation of the exponential function it times Sn over sigma times the square root of n, which is just here, is just 1 minus t squared over 2n plus the infinitesimally term with respecting to 1 over n to the nth power. By lemma 2, the last expression is just the c. Here is just t squared over 2, so it goes to e to the c, which is just the standard normal distribution. Sn goes to infinity. As in the proof of weak rule of large number, we will prove a general result for triangular array to get the most familiar law, the Lyapunov theorem. It's called the Lindenberg-Feller theorem. It states as the following: for each n, let xn, m, and 1 is smaller or equal to m, which is smaller or equal to n, be independent random variables with expectation equals 0. Suppose that first, the sum over m of the expectation of x squared goes to sigma squared, which is greater than 0, and 2, for all epsilon greater than 0, the limit of Sn approaches infinity of the sum over m of the expectation of the absolute value of x and m squared, and it is greater than epsilon, is equal to 0. Then the sum goes to sigma times the normal distribution. Sn goes to infinity. In other words, the theorem says that a sum of a large number of small independent effects has approximately a normal distribution. Notice that this is not identically a sequence. The xn m. Actually, we can get theorem 1 out of this one. We can let y1, y2 be identically independent sequences with expectation equals 0, and the square of the variable's expectation is sigma squared, which is the variance, is positive and finite, and let xn m be ym over square root of n. Then the sum over m of the expectation is sigma squared. By the supposition, if epsilon is greater than 0, we have our 2 here, so we can drag the n from the sum out because they are identically distributed, and thus we know that the expectation goes to 0 by the dominated convergence theorem. Notice here is 1/2 times n. We are now going to prove the theorem. Let phi and m be the expectation of the E to the it times x in m, and sigma in m squared is the variance, we notice that it is sufficient to show that the product of the characteristic function over m goes to the e to the negative t sigma squared over 2. Let z in m equals phi in m and w in m equals 1 minus t squared times sigma squared in m over 2. By the corollary 1, we know that the absolute value of z minus w is smaller or equal to the expectation of the minimum. This just means the minimum of first one is t times x in m to the third power, but it is in absolute value, so it's definitely positive. Or 2 times t times x in m squared, which is smaller or equal to. We break off the two parts, the expectation of t times x in m to the third power, which x in m is smaller or equal to epsilon, plus the expectation of 2 times t x in m squared, and it is greater than epsilon. And we drag it out, we know that it is smaller or equal to epsilon times t third times the expectation of x in m squared, and x in m is smaller or equal to epsilon, plus we also drag this out, the expectation of x in m squared and this guy is greater than epsilon times 2t squared. We sum over m and let n goes to infinity. Use the two properties. We notice that the limit of the supremum of the sum of z in m minus w in m's absolute value is smaller or equal to epsilon times t third sigma squared from this equation. Since epsilon is arbitrary, it follows that the sequence converges to 0. So here this sequence converges to 0. Our next step is to use lemma 3 with theta as 1 to get that this 1 goes to 0. To check the hypothesis, notice that since the characteristic function is smaller than 1 or equal to 1 by the properties for all n and m, for the terms in the second product, here we notice that the variance is smaller or equal to epsilon squared plus the expectation of x in m squared, and it is greater than epsilon. Because epsilon is arbitrary, so the condition 2 implies the supreme, of course, is m of sigma squared n m goes to 0, and thus if n is large and 1 is greater or equal to 1 minus t squared sigma n m squared over 2, which is greater than negative 1 for all m, because here's the absolute value. To complete the proof now, we apply lemma 2 with the Cmn equals t squared times sigma n m squared over 2. We can actually generalize lemma 2 to the triangular array with index mn or nm. We have just shown that the supreme of the variance goes to 0, so 1 implies the sum over m of Cmn goes to sigma squared t squared over 2, which is the negative 1. So the product right over here goes to exponential function, and so this is proven and the proof is complete. Finally, we are ready for the last and the most familiar central limit theorem, the Lyapunov theorem. Let an be 1/2 of the variance of the sum, and if there is a delta which is greater than 0, so that this condition follows, then Sn minus the expectation of Sn of An goes to the normal distribution, which have sigma and mu equals 1. To prove this, we can let the triangular array just equal to one index m and over An, which is xm minus the expectation of xm over An. We just need to show xm suffix nm suffix the condition of the Lindenberg-Feller theorem. So first one is obvious. You can just plug this in and notice that An is the 1/2 power of the variance, and they cancels out because of the sum, which is just 1. The second condition is a little bit complicated. For some given epsilon which is greater than 0, the sum over m of the expectation of x and m squared, and it is greater than epsilon, is equal to the integral by definition, the expectations definition, when x and m is greater than epsilon of the squared term d mu, or probability here. It's the probability measure, which is equal to 1 over An squared times the sum over m of the integral when xm minus the expectation of xm is greater than epsilon times fn of the xm minus exm squared d probability, or dp, which is smaller or equal to 1 over An squared times the sum over m of the integral. The boundary doesn't change, and we know it is smaller or equal to the squared term of xm minus the expectation of xm over epsilon times n times itself squared dp, which is smaller or equal to, we drag out the epsilon terms. Notice here's delta, here's 2 plus delta. Actually, the delta 1 over something to the delta's power is being dragged out of the integral and the summation, so it is smaller or equal to 1 over epsilon to delta times 1 over alpha n to the 2 plus delta times the summation over m of the integral. Notice here is also 2 plus delta of this quote-unquote variance dp, which goes to 0. After proving the law of large numbers and the central limit theorems, we are going to talk about the explanations and the connections of law of large numbers and central limit theorems. The weak law of large number tells the improbability convergence, which means when the samples number n is really large, we know that the probability of the absolute value of xn minus m is greater than epsilon goes to 0. But the thing we don't know, or we can't be sure, is that is there infinite or finite m prime which is greater than n? It is xn prime minus x. It is greater than epsilon. But the strong law of large number has to almost surely convergence, and it says the probability of x equals xn when n goes to infinity is 1, which means if there are only finitely many xn prime minus x is greater than epsilon. So the strong law of large number applies the weak law of large number, and the weak law of large number is a special case of the strong law. The two laws of large numbers both tell us about the average or the mean or the expectation of the samples tends to the expectation. But we know, do we know the expectation? No, we don't. So we need the central limit theorem. The central limit theorem tells us the exact distribution when the sample's number is very large or n approaches infinity, and the law of large number tells us the normal distribution's bell curve, where is the center of the bell curve. And the central limit theorem and this law of large numbers tells the distribution of the sum of the random variables. In other words, it's the convolution of the random variables. You can get a really well visual perspective of this sum or the convolution on 3 Blue 1 Brown's channel. And here is the proof and the connections. Thanks Grant and 3B1 Brown for offering the platform, and thanks my mother for standing beside me and giving me support to make the video. And thanks you for watching. I'm looking forward to some feedbacks and improve myself